Okay, thank you very much, Mr. Chairman. This is Kato. Today I'd like to talk about enhancement of hydrogen sensing with a multi-reflection Raman scattering. And first of all, gas sensor using Raman scattering is the Raman scattering, as you may know, is a phenomenon which incident photon to materials are scattered at a different specific frequency than the incident photon. So when we excite the material with, for example, 355 nanometer laser, the Raman scattering wavelength will be different with the gases like this, or even with a solid material, of course. But we are focused on the gas sensing, especially hydrogen, which is 416 nanometer in wavelength. And conventional hydrogen sensor is not so effective in a very high humid atmosphere. So, for example, water is 407 nanometer, so we can distinguish the water and hydrogen. And also the luminous phenomenon is a very fast response, so this detection is very fast. And as I said, it's good in high humidity. And the previous work has been done with a single laser beam, one pass laser beam in a far distance. So we could, they could try to measure the hydrogen gas in a far distance for example of accident or a dangerous case. And the tested result was about 7.5 meter away. Hydrogen was detected, and the limit was about 0.6%. And as you may know, Raman scattering intensity is very weak compared to Rayleigh scattering, which is about 1,000 times weaker. So we need to have a good sensing. So here we try to enhance the intensity with multiple reflection using two concave mirror like this, and then we have lots of laser beam hitting the gas in the middle, so we therefore we can get higher intensity. And this is the simulation result. We use two different focal lengths and diameter mirror like this, and then according to the simulation, about 30 to 40 times reflection can be achieved. And this is the experimental result, which is quite similar to the simulation. And this is the experiment apparatus. First, we have a laser beam coming out from here, which is here, semiconductor laser. And then we focus with a lens and then put into the cavity with two concave mirrors, which mirrors M1 and M2 is here. And then below, inside this cavity, we spray the gas and then detect the Raman scattering by the lens, which is here. And then focused to the photomultiplier with a 416 nanometer filter, which is for hydrogen detection. This is the side view of the from the photomultiplier here. We spray the gas from the bottom to the top, and this is about we use the 5% hydrogen mixed with the nitrogen gas, and this can be varied by diluting. And this is the result. First, the result of the single laser beam pass without multi-reflection. And this is the signal. The black one is without hydrogen and the green one is with hydrogen. So you can see the light intensity here is increased. So we subtract the background and then get the hydrogen Raman scattering signal like this. And the peak was about at 6 nanosecond, and this is explained by the light traveling time from the laser exit to the gas here is about 60 centimeter, which takes about 2 nanoseconds for the light to travel. And after the Raman is scattered, we have the detector at in a distance of 120 centimeter, which takes about 4 nanoseconds. So totally 6 nanoseconds time is necessary. That is matches the result here. And next we have the multi-reflection compared with one pass laser light. Since the reflection continues longer time, we have larger hydrogen intensity like this. And up to 16 nanoseconds, we have about 35 times large signal compared to this single laser beam, which is about same result from the simulation. We also checked the linearity of the gas concentration with a signal intensity, and as far as up to 5%, we dilute with nitrogen, and then we have a good linearity with the signal intensity, and we can estimate that up to 100% hydrogen concentration, we can detect this hydrogen with this technology. And the lowest concentration we could obtain was about 0.1 volume percent of hydrogen. Next, I would like to talk about the multiple gas detection. When we have the bandpass filter tilted like this, we could vary the transmittance wavelength according to this equation. So when we varied the tilting angle theta 1, we could have a different transmittance like this using the white bulb light as a light source. When the filter is not tilted from 0 degree to tilted up to 55 degree, we could vary the transmittance wavelength like this, going down. And for example, the filter is for hydrogen, so without tilting, we have a hydrogen detection Raman scattering wavelength at 416. But as we tilted, we could detect different wavelength, which is around here. This is the water Raman scattering. Around here is methane Raman scattering, and so on. So with this system, we can detect a different type of gases also. And we did the experiment, and then here is the rotational degree theta 1. And as you can see, hydrogen here, peak here, and then methane peak here, we can detect. So at the same system, we can detect various gas, for example, hydrogen and methane. And the methane concentration from this signal peak was estimated about this much of the volume percent. And using the infrared methane detector, we could detect about this much, which is relatively close enough to detect. And this is the ideal multiple detector experiment, which is we are going to perform. And since the optics with the lens is sensitive to humidity or other kinds of gases, so it is ideal to put the sample gas into a quartz container, for example, and then separate the optical system with the gas, and then detect the Raman scattering, and rotate the bandpass filter, like as I said here, with the different wavelength transmittance, so we can detect different gases. And if the laser is now getting better and operated with battery, and this system can be miniaturized, very small, so this whole system could be a handy type in future, I hope. As a conclusion, amplifying the Raman signal from the hydrogen gas was investigated by using multiple reflection laser beam using a two concave mirror cavity. And hydrogen Raman signal intensity was increased more than 5 times, 35 times, and the lowest limit detection was about 0.1%. And good linearity was obtained between hydrogen concentration and Raman signal intensity. And the last multiple gas detection was performed by a rotational bandpass filter, and the mixture of methane and hydrogen gas can be distinguished and quantified. Thank you very much for your attention.